So now we start with the computation of our model of our Laffer curve. So what we have in mind is that we would like to study the Laffer curve as a function of the tax rate on labor income, which is the sum of the tax rate on wage income and the social security contribution rate. So therefore, I would like you to start your Gauss program. And it should look something like this. You are in the edit mode, and depending on the version of Gauss, the screen looks like this. I assume that you have a more recent version of Gauss. Gauss 1516 will do, so that you can display the new graphics that comes with more recent version of Gauss. Please load Laffer.gss into your working directory. You can change the working directory in the upper menu bar and just set it so that all files that you download from my homepage are contained in this directory. This includes Laffer.gss, the Gauss program, two procedure files, which are toolbox.src and function.src, which we use for the computation of the nonlinear equation problems. This also includes the Excel file survival prop US XLS, where we store the demographic data. And finally, as an FMT file, the file ef1.fmt, where the Hansen age efficiency profile is stored so that workers in older age become more productive up to age 50. We will use it in the computation below to have a more realistic labor supply profile over the life cycle and more realistic savings and income over the life cycle. Now let us first run the computer program Laffer.gss to see if it works. So for this reason, press the green arrow or F5 to run, or Control R to run the program. And first you will find the display of the survival probabilities in the benchmark year. So we have chosen the year 2010. You can set it as you like. And as you can see, survival probabilities decline with age. So at age 20, the survival probability is almost 100%, and at age 88 it declines to 88%, and at age 89 you die for sure. So we have a 70 period overlapping generations model in the end. Now you have to press any keys. We have introduced a wait statement in the Gauss program. Next you find the efficiency age profile, which is hump-shaped. It's taken from Hansen. It peaks at the age 50, so efficiency increasing until this age. Afterwards it's declined, but at a smaller rate than the initial increase after age 20. We have normalized the efficiency, though that average efficiency is 1 in over the life cycle. You have to press another key on the keyboard. And next, the model is computed for the case of exogenous labor supply. Labor supply is set equal to 0.25 in each cohort. And we computed for the 46 period model first. So we have 45 cohorts of workers and 1 cohort of retirees. And then we increase the number of retirees by 1 in each iteration. So here on the right hand side in the output column here you find the number of periods in our model. So now the model is computed for 68 periods, next 69 until 70, and then this stops. It's used as an input into the 70 period model with endogenous labor supply, which is computed next. And here we find the life cycle behavior of the households in the model 70 period OLG model with endogenous labor supply. And this looks very plausible. So you should always check these intermediate results and see if they make sense. You should look at the individual behavior, at the optimizing behavior, and see, well, that the assets behave as expected. The agents increase savings until the age 60 or 58. Afterwards, they decline. Remember that efficiency peaks at age 50 and declines afterwards. So the biggest part, of course, of savings occurs during the time of high efficiency, during age 30 to 50. And after age 60, it declines until they die. If an agent dies prior to age 90, well, then the leaves bequest, and the bequest, as we described before, will just be collected by the government. You have to press another key and find the consumption age behavior in the next graph. So consumption increases until age 64, until agents retire, and at age 65 there's a drop in consumption. This drop results from the utility smoothing behavior of the household. Remember that at age 65 leisure increases to 100%, labor declines to 0. So this increases utility, and to offset this effect and smooth utility over lifetime, households decrease consumption. Finally, at age 80, consumption declines again, and this is caused by the increase in the death probability, or put it otherwise, stated otherwise, the decline in the survival probability. And then from the Euler equation, it follows that you should decrease consumption. This makes intuitively sense if you know, well, chances are getting smaller and slimmer that I will survive, so why shall I keep up all these savings, just run them down faster so that I can enjoy while I'm still alive. And finally, you see the labor supply profile of the household over the age 20 through 64, which is his final period of working period. It peaks at age 30. Remember, there was a king in the efficiency age profile that is also reflected here in our labor supply profile. Afterwards, it declines. So we have two effects here on labor supply. Our efficiency increases until age 50, but this increases our labor supply due to the substitution effect, but our wealth is also increasing until age 60. So this wealth effect, this income effect, reduces labor supply, and the net effect is shown in this diagram. So labor supply increases until age 30 and afterwards declines. Now we use this aggregate model with endogenous labor supply and use it to calibrate the discount factor beta. And we calibrate beta so that the real interest rate on bonds is equal to the real interest rate on capital after depreciation, and that it's equal to 4%. And in order to get this return, we need to impose a value of beta equal to 1.0371687. This concludes the calibration of the model. And in the next step, we'll also look at the mean labor supply, So the mean labor supply is 0.3085. So the labor supply is in close to a value which we were targeting. So in dynamic general equilibrium models, which are based on the Ramsey model or the overlapping generations model, we would like to get an average labor supply of 30%. Some choose a labor supply of 25% like Trabant and Ulich, but we are very happy with this value that for the preference parameter kappa from the model of Trabant and Ulich, which is set to 3.6, we derive a mean labor supply of 30%. So that's very realistic, and we do not have to change the preference parameter of Trabant and Ulich to get realistic labor supply values. And once we have computed the calibrated the factor bidder and have observed that our labor supply is decent, behaves decently, we can start the iteration over the wage tax tau n to compute the Laffer curve. You have to press another key on the keyboard, and this provides you with the Laffer curve X as displayed in the slides. So this concludes the execution of the problem, and now we look into the computer code in more detail. So switch back to the edit mode by just clicking the edit sign here on the left hand, and let's look into the computer code. The computer code is rather lengthy. So I have written some 1,000 lines or 1,200 lines, and you could have written it much more elegantly, reducing it to a length of perhaps 200 lines. But this way it's much easier to understand and to follow through if you are new or not very sophisticated in the use of Gauss. So this is an easy to debug code for beginners. So in the first part I have entered between two @ signs the description of the program, so its name, when it was written, and what it does. And of course, as always in the beginning of the program, I introduce a new statement and a clears all statement so that the memory is cleared and no variables are preset, or the variables are preset. You should always do this. Now we distinguish 8 steps in the execution in this algorithm. In the first step, we set the numerical parameters. In the second step, we load the demographic data from the Excel file survival props US Excel XLS. In the third step, we set the model types. So for example, in line 55, we specify the year. So we use the demographic data from the United Nations for 2010, but you can also specify another year, let's say 2015 or 2050 in this line, and compute the Laffer curve in the future years, in the projected year, and see if the fiscal space, for example, shrinks. So how the demography and the demographic transition is affecting our Laffer curve, our possible tax revenues. Just make sure that this number here is a multiple of 5, so 2010, 2015, 2020, because the population parameters are only available for a period length of 5 years. In step 4, we calibrate the model. So we use the parameters from the model of Trabant and Ulich in the Journal of Monetary Economics 2011. So for example, we set the production elasticity alpha equal to 0.35. We use their values for the tax rates and the values for the government consumption output ratio or debt output ratio, for example. And also their preference parameters. And we specify if we have case of exogenous growth of 2% annually or not. It makes, of course, a big difference once we introduce pension system, which are absent in the model of Trabant and Ulich. In a pension system, the return of the pension system for the individual depends on 2 growth rates. One is the economic growth rate, because if I contribute today and I will get from this pay-as-you-go pension system a pension that depends on the contribution of future cohorts, and they will have a higher wage rate due to the growth rate, I will benefit. And of course I benefit from population growth, because more young people in the future will provide for fewer older people if I have high population growth. So these 2 parameters, population growth and the economic growth rate of 2%, will make a difference, and you are invited to study it by specifying either case growth equal to 1 or case growth equal to 0 in the header in step 1 to find out about these differences. In step 5, we start to find an initial value for our nonlinear equation problems. And as described in the previous part of the tutorial, we start from a 46 overlapping generation models where 45 cohorts are workers and the last cohort is a cohort of retirees. The reason to do this is because this model is very akin to a Ramsey model with finite horizon. We have just one cohort of retirees, which of course has only a small mass of agents in the total population, and therefore we can use the steady state capital stock in the Ramsey model as a starting value for the steady state aggregate capital stock model in this overlapping generation models. And this is really a tremendous help. And we will see that it's no problem in this case to find the asset age profile of the workers and the retirees. So we have no problems to compute the solution to this kind of problem. And in the next step, we just increase the number of retirees cohorts from 1 to 25 so that our model has 70 cohorts. And we do this stepwise, incremental increases by just one cohort, and we can use the solution of the previous OLG model with one smaller one missing cohort, one lesser cohort, as a starting value. In the next step, we add endogenous labor supply, and as initial guess, we just use our steady state labor supply from the Trabant and Ulich model, which is 0.25. And we will find that this works very well, and we will solve this nonlinear equation problem in the procedure SS and lab, providing the initial value for the age wealth profile and for the labor supply age profile. In step 7, we calibrate bidder so that it's the real return on bonds and on capital is equal to 4%. So far we have used a value of bidder that follows from the Ramsey model. Now we calibrate it so that it's adequate for our overlapping generations model. And finally, in step 8, we compute the Laffer curve. So we have calibrated bidder, we have our benchmark values for government consumption, our benchmark values for government debt. We will keep this constant while we iterate over the equilibrium for different values of tau n, our tax on wage income. And we store these values and finally display the solution as our Laffer curve. This is an overview of this rather extensive program. So let's go through it in the debug mode. Therefore, start the debugger by pressing the red bug. And let's go through it line by line. In line, and you can move around in the debugger by pressing the arrow keys in the top menu, or by pressing the function keys, for example F1, F9, you get to the next line. So the number of maximum iterations over the aggregate capital stock is set to 50. The tolerance of the nonlinear equation solver is set to 10 to the power minus 6, and we use an iterative dampening procedure to update our date of the aggregate capital stock of 0.9. So this means if we start with the value of k, let's say 1.0, and find a new value of k equal to 2.0, we just use 1.1 as our next guess. And we also provide our nonlinear equation solver with a machine epsilon of 10 to the power minus 30 in line 26. We also tell our Gauss to include toolbox.src and functions.src, which contains our nonlinear equation solver. In the next step, we just clear the screen and load the demographics. So for this reason, we read the data from the Excel file survival props US, which is stored in the cells F22 through AI37. And since the survival probabilities are stored in somehow unconventional order, so starting from the oldest going down to the youngest, we have to reverse the order that's done with the command ref. If you do not know a specific command, just use the help function. You can use this also in the debug mode, so just press the help menu on the top, go to help. So, and if you want to look up a specific command, the syntax, for example, just type, for example, ref, and it tells you that ref reverses the order of the rows in a matrix. So this is what we do in our case. Now go back to our debugging mode by pressing the Control 4 or switch to debug here. So let us take a look at our survival probabilities here. You can see, for example, in the first line, in the first cell 0.993, this is the survival probability of the 20-year-old in the year 1950. In the next column you find the value 0.9935. This is the survival probability of the 20-year-old in the year 1955, and so on. We also load the population growth rate from the survival props US Excel file. And here our data contains the year 1950 and the survival and the population growth rate 1.581% in the year 1950, and it's also projected up to the year, I think, 2095. And we have three scenarios here from the United States, from the United Nations: the medium, low, and high variant. Of course, until the year 2015 they coincide because we can observe the data, and only after this they start to diverge because it's based on projections. You can read more about this in my book on public economics, where I describe some of the data in the 6th chapter. Now we do some smoothing here of our data. We use moving averages over 4 periods, and here we specify the case if growth or no growth of case productivity equal to 0. This means we impose the hump-shaped age efficiency profile from Hansen. We use the case with exogenous growth, and we use case 1 where we calibrate the pensions such that the replacement ratio is equal to the empirical one. You have other options, for example, that the pension contribution rate is equal to the empirical one. We opted here for the first option, but you can change this as you like. So we use the medium variant scenario of the United Nations, and we still have to calibrate the parameter beta in our model below. So we assign the value 1 to the parameter case beta calib. This is our benchmark case. We save it, and here we specify the number of 5-year periods in the survival probabilities data from the United Nations. So we have 15 periods. In our model, we want to have 70 periods starting from age 20 up to age 89, and the retirement starts in period 46, which corresponds to year 65 in real life. NR is the number of retirees, D is the number of cohorts for the retirees, and NW for the workers. We load the efficiency profile from Hansen, which is stored in the file ef1.fmt, which you also store in the working directory. And in line 81, we normalize it to 1 so that average efficiency is equal to 1. In the next 10 lines, 88 through 98, we convert the 5-year, we convert the moving averages over 5 years into our survival probabilities. So let's go through this. So our population growth rate is now given by 0.00946 or 0.9%. That's our population growth rate in 2010, which is the average over the period 1990 through 2010. Similarly, the survival probabilities are the average survival probabilities during this period 1990 through 2010. And these are 5-year values, so we have to transfer them to annual values, which is done in the following lines 103 through 110. What we do is we use a cubic spline interpolation between these values and convert them from 5-year to 1-year rates. For those of you who do not know cubic spline interpolation, I would like to ask you to read the specific chapter in any good numerical mathematics book. I recommend the book by Ken Judd on computational economics from the year 1998, where you can find this procedure. If you do not want to get into the details, just ignore it. Just look at what we got in the final version here, our SP1, which is our annual survival probabilities, and it's a 70 for our 70 generations, and we also included the last generation where survival is 0. And next we plot the survival probabilities that we find. You already know this picture here, and go back to the debug mode. We have introduced a wait statement, which we just press a key, and next you find the efficiency age profile that you loaded from ef1.fmt. You can also suppress this by pressing any key and continue here. We save our survival probability in the variable SP. This concludes step number 3. Now let's get to step number 4, where we enter the calibration. So we take the parameters from Trabant and Ulich, alpha for the production elasticity of capital, delta for the depreciation rate. We will set beta so that the government bond return is 4%. The wage tax is equal. The wage tax plus the social security contribution rate is equal to 28%. This is stored in tau L bar as well. The capital income tax rate is 36%, and the consumption tax rate amounts to 5%. We use tau p as our guess for the social security contribution rates of 12.4%. The US value is close to 12%, so this will be calibrated below so that tau p balances the social security budget. And the replacement ratio is set equal to 35.2%, which is the gross replacement ratio, meaning the ratio of pensions relative to gross average wage income in the US, and this is taken from OECD. We take the debt output ratio and the government consumption ratio of 63 and 18% from Trabant and Ulich. The fresh labor supply is relatively high. It's set equal to 1, so you may want to apply some sensitivity analysis later on and use values that are perhaps below 1. So you also, in macroeconomic analysis, we also use values of 0.2 or 0.3, so check this out. And we start with an initial steady-state labor supply of each cohort of 25% and an intertemporal elasticity that's equal to 1 over 2.0. And we use the preference parameter kappa 3.619 that's also used by Trabant and Ulich, and we will find that this is really a good value, so we will get an average working hours of 30%, which is pretty close to what we would like to find out in our model. And we set the growth rate equal to 2%, so our growth factor is 1.02. Now we have to choose an initial value of our bidder, and this follows from our Euler equation in the case that marginal utility lambda is constant. In this case, beta is given by the growth factor to the power eta divided by the gross interest rate of government bonds. And we will use this as our initial value. Of course, we will find that's different from the Ramsey model, that our discount factor depends on age, and therefore we have to calibrate beta. This is not necessary in the Ramsey model, because in the steady-state Ramsey model, the marginal utility of consumption is constant. And we also take the time that we use for the computation. This concludes step 4. Now we get to step 5, which is a little bit more extensive. So we start with an initial guess of aggregate labor supply, and since everyone is working 0.25 and almost all population consists of workers except for one cohort, so of course it makes sense to use 0.25 as initial value. The capital stock is simply taken from the one in the Ramsey model. So if you look at the Euler equation in steady state, you find that capital stock is provided by the equation in line 198. And we will use this because we assume, well, if we look at a 46 period overlapping generations model where just one cohort is retired and all others are working, why shouldn't this behave so much different from the Ramsey model? And in fact, we will be right with this kind of assumption, and so we can come up with an initial guess. And of course, that's the problem with such large scale models, how to come up with a good initial guess. Start from a simple model like the 46 period model with exogenous labor supply, and then add additional elements. And this of course has the added advantage that at each step you observe if there's a dramatic change in behavior or not. And if it is, well, perhaps you have done a programming error. So this also helps you to debug your program. Now we just store, we use k-old and n-old, two variables to compute the initial change in the capital stock from the iteration over the capital stock. So this is just to have a measure of convergence here. And it needs to be different from k-bar and so that we don't stop our iteration. We compute the wage and the interest rate from this. So let us jump into the procedure wage rate. So for given values of k and l, uppercase L, we can compute the wage as a marginal product from labor. Jump back by pressing the appropriate arrow F10. And similarly, we can compute the marginal product of capital. So we let's also step into this procedure, and here you find the marginal product of capital as a function of capital and aggregate labor, and jump out of this procedure. Production is also computed with the help of the procedure production. So this is simply the Cobb-Douglas case that we consider here. And for our value of production, we can compute the depth level for our calibration, for our depth output ratio, big B, and from this we can compute another endogenous variable in our model, the share of capital and total assets. And total assets are simply the sum of capital stock and debt. And we initialize our transfers as 1% of output. This is really in innocent assumption. We doesn't matter whether we use 0 or 2 or 3 or 5%. We could also use the empirical values of the United States. In our computation, we will we'll compute transfers endogenously so that the fiscal budget is balanced. And our pensions are simply the replacement rate ratio of 35% times our average wage income, which is approximately the wage times aggregate labor supply. And now starts our iteration over the number of retiree cohorts. So we start our number of we compute our model for 46, 47, 48 and so on cohorts, which are stored in the variable NH grid. And we start with the first entry with 46 periods. So IH is set equal to 1 in this loop, and our number of periods in this model, which is called NH, is set to 46. In the next 6 lines, we compute the steady state, the stationary mass of this economy. So let's start with any guess for the mass of the first cohort. Let's say it's 1, and in the next period, the 20-year-old, I have the mass 1, and the 21 have the mass of the 20-year-old times the survival probability divided by the population growth. So the 20-year-old grow by pop growth and die and only survive with probability of 99.91%. So in this case, we have computed the mass of the 20-year-old with 0.9897, and we can continue so up. Let's jump to line 233 by moving to this line, run to cursor, pressing the appropriate arrow key in the menu bar so that we do not have to run through these iterations, 46 iterations. And our final mass looks like from 1 declining to 0.81 at age 20 and so on. And we normalize it to 1 so that our total mass of all cohorts in this economy is equal to 1 by dividing through the sum of all mass. So now we have the stationary measure of each cohort. So the 20-year-old have a mass of 0.0278. The 21-year-old have a share of 2.7553% in total population, and so on. This is our stationary measure. And if you do not know how to compute such a thing, why we have used this formula, please look it up in my book on public economics. Next, we initialize the agent's policy function, the one on optimal assets, consumption, and labor supply. Of course, in the case with exogenous labor supply, we set it to a constant 0.25 in each cohort of the workers. Okay, now it's the first time we run this, and we have to, so IH, the variable, is equal to 1. And we have to come up with a guess for the age wealth profile, which is our endogenous variable. So we are inspired here by former results on overlapping generations model, and what we find is that usually individuals increase their savings up to retirement or close to retirement and then decrease their savings over the remaining lifetime. So to get an average capital stock of K bar, this means, well, we start from zero for the 20-year-old, and to get an average of approximately K bar, we have to accumulate twice K bar as our maximum capital stock in the last period as a worker. And for the remaining life, which is just 1 year, 1 year in retirement, we assume, well, that we reduce it linearly until we die. So this is we divide it by 2, so we just save half of it for the very last period of our life. This is our initial profile for the capital stock. So we will provide this value K initial as our value to the solution of the procedure SS exogenous labor below, which is our nonlinear equation for the overlapping generations model with exogenous labor supply and NH periods. So let's step into this procedure here. We provide the age wealth profile to this procedure as our endogenous variable x. We store it as the variable asset, and of course in the first period, at the 20 years, start with a value 0, and when they die they leave 0 bequest at the end of 46 periods in case they survive up to the last period. The K share is the exogenous parameter, which is the share of capital in total wealth. We assume that each cohort has the same share of capital and bond as the aggregate economy. Because we have no risk, this portfolio choice is indeterminate, and this assumption does not have any implications for our computation here. And the remaining assets are held in the form of bonds. Our labor supply is simply equal to 0.25 at each working age. And we add the number of retirees age in the form of zeros, so this will be used in our nonlinear first order equations where we specify a labor supply of 0 for the retirees. Now we compute the consumption, and we use the budget constraint of the workers in line 89. So net income 1 minus tau and tau p times the wage times the efficiency. Efficiency, for example, of the 20-year-old is 0.59 times the labor supply. That's our net labor income. Then we add the capital income and the income from government bonds, and also government transfers. You notice that we are using the stationary version, so we also know that stationary variables here have to be redefined so that the government bonds in levels and capital stock in levels grows by the factor y grows equal to 1.02. And we have to pay consumption taxes tau c and consumption. Similarly, in lines 901 and 902, let's run to this line by posing the cursor here. Oops. And compute the consumption of the retired agents. So they do not receive labor income, wage income, but pensions instead. That's the only difference here. And in the very last period, so pose your cursor on line 905 and run to the cursor. the budget constraint changes because we do not accumulate any savings or assets for the age 91, because at this time, or sorry, for the age 47, because at this age we are dead in the 46 period overlapping generations model. So this terminates our computation of the consumption, and now we use the Euler equations as our first order conditions. So we have 46 periods. We live 46 periods. This results in 45 Euler equations, and the 45 Euler equations are matched by our 45 endogenous variables, which are the capital stocks at ages 2 through 46, which are different from 0. And the Euler equation here can be found in the slides. Here, notice that we use labor as here because we also specify marginal consumption. Let's step into marginal consumption here as a function of consumption and labor, and labor is 0 for the retirees. So this utility function, instantaneous utility function, here specified as a marginal utility from consumption, is taken from Trabant and Ulich as explained in the slides. So this has the neat feature of a constant Frisch elasticity, and the utility function is in accordance with long-run growth. So let's step out of the procedure you see, marginal utility again, and and return out of this procedure SS exogenous labor, and this completes our computation of the nonlinear 45 equations in this case. Okay, so this was a check to see if the procedure SS exogenous labor is in fact computing the correct output, the correct returns. Now we do the iteration over the aggregate capital stock. So we start with our guess of K bar, which comes from the Ramsey model, and compute our criterion if if we are close to the solution or not. And of course we have specified K old and N old in such a way that this criterion is equal to 1, so that it's not close to 0. And we iterate over this capital stock maximum iteration of 50 times. We start by computing the wage and the interest rate, and we compute the exogenous, the solution to the 46 period overlapping generations model here by solving the nonlinear equation problem, SS exog labor, and computing as a solution our asset age profile as described above, as we went through the computation in the procedure SS exog lab procedure. From our solution is stored in the variable of the optimal assets, A opt, and we add 0 at the beginning and at the end, because people start with 0 capital supply assets and end with 0 assets at age 7 at the final period of their life. We compute the individual capital and bonds as a share of these assets. We again compute in the next line 302 up to 319. We compute again consumption. So let's post the cursor on line 324 and run until this line. We compute the new aggregate asset. We compute the new capital stock. And now comes the updating of the capital stock. So this is a Tatanemont process here. We start with K bar, K new, sorry, K old, which is stored, K bar, which is stored in K old. find a new value of the aggregate capital stock, which is simply the sum of the individual capital stock, and use as a new value K bar. So we started with K 0.09501184, find a new value of K new 0.998, and using updates parameter of phi equal to 0.9, we get a new value of K bar that's equal to 0.955, and we will use this in the next iteration. We also update our aggregate consumption here, big C, which we will use to compute total taxes. Total taxes are wage taxes, tau n times wages times aggregate labor. Taxes on capital income, tau k, which is on interest income on capital. Depreciation is tax exempt, so we can reduce our tax payments by depreciation. And we have to pay taxes on consumption. And the government also collects accidental bequests if people die before age 46, and we store these accidental bequests in the variable bequests here. Sorry. And this is the expression of bequest. So it's the capital stock plus the interest rate earned on the capital stock here, the net interest rate. This equation is also derived in my book on public economics, why you have to include the net interest income in the computation of the accidental bequests. We compute production, the values for government consumption and debt, and compute the new transfers that results from the fiscal budget. So the revenues consist of taxes, bequests, and new government bonds minus old government bonds and interest rates minus government consumption. And we update our transfers again with the parameter here, updating parameter phi found by new and old transfers bar and the new transfers. And finally, we have to compute the new labor supply and the new share of capital in our portfolio. Now, in the case that we calibrate Bidder, we have to update Bidder, and this is done with the help of the Euler equation described here in the comment. So we have two Euler equations, and if you can use the Euler equation, the one Euler equation with respect to the capital stock as our old version for the beta, and substitute the left-hand side term on this equation in the Euler equation for the government bonds, we have an expression that relates our new value of beta to the old value of beta, and that's provided in line 362. So let's go through this. And finally, we compute the mean labor supply here. Unsurprisingly, the mean labor supply is equal to almost 0.25, and this is different from 0.25 specified above because we also include the efficiency labor, so that we have that the pensions are related to average labor income, which is the product of the wage times the hour wage, which we set to 0.25, times the individual proficiency, the age efficiency, and of course, as a consequence, mean labor is not equal to 0.25, but it diverges a little bit from it. And we specified case pension 1, so where pensions are proportional to mean labor earnings, and we set the new pension simply as the replacement ratio times the mean wage income wage times mean labor to compute the new pension and update update the parameter tau p, the social contribution rate, accordingly. So in line 377 we have the social security budget, a social security constraint, compute the new social security contribution rate, equilibrium rate tau p, and update tau p accordingly. And finally, we also update pension. Now in this iteration over the aggregate variables, the capital stock, the pension contribution rate, pensions, aggregate labor supply, is done a number of maximum iterations of 50, and we find that it converges neatly. And when we have computed this equilibrium, we increase the h by 1 here in line 222, and we do the computation of our overlapping generations model with exogenous labor apply for a model with an additional cohorts of retirees. So this continues over another 25 iterations until we have computed the model with exogenous labor supply for 70 periods. So let's jump into line 400 where this is completed. So this will take 1 or 2 minutes, and then we just display our equilibrium values, observe whether our computation is accurate. So we use our solution K initial and see if indeed our procedure SS exogenous labor supply returns 0. So 69 entries of zeros for our 69 endogenous variables K of the steady state assets of the cohorts for our 69 Euler equations. And this completes our computation of the case with exogenous labor. Next step, we go on to compute the case with endogenous labor, and therefore let me jump into the procedure that describes this nonlinear equation problem. So we go down all the way to line 925, SS endogenous labor. We provide again the assets, the individual asset as the individual endogenous variable, but now we also supply labor S and a guess for our labor supply of the workers during age 20 through 64. So we have an additional 45 individual endogenous variables here, and therefore we have to add 45 new nonlinear equations here, equilibrium conditions, and this is done in lines 967 through 976, where we add the first order condition of our workers with respect to the labor supply. So where we set the marginal utility from consumption times the extra wage that we get if we work an additional hour equal to the disutility from labor. Besides, this procedure SS endogenous labor is exactly the same as the one for exogenous labor, and we solve it in step 8 and in step 6, and just do the same routine that we did for the case of exogenous labor supply. So we use an updating scheme for the aggregate variables, for the aggregate capital stock, for the social security contribution rate tau p, and for pensions and aggregate labor and so on, and the K share, the share of capital and total assets. And when we have finished with this computation, we display the individual policy functions for the assets, consumption and labor supply over lifetime and working life respectively. So now we have computed this, and let's jump to line 626. By moving the cursor to line 626 and pressing the appropriate arrow in the top menu. In line 626, we invoke the procedure SS aggregate capital, so which stands for steady state aggregate steady state for calibration. What we provide as input into this procedure is the individual capital stock asset level. Let's just I have to press. Okay. The individual policy function with respect to labor supply, so for example the 20-year here supplies labor of 0.25. Aggregate capital stock, which we take from the model with endogenous labor supply. Aggregate labor, which is equal to 0.2288 in the model with endogenous labor supply. Our value for total debt, 0.23, our value for the social contribution rate, for transfers, and for our initial value for bidder, 1.039626. And now let's step with this guess into the procedure SS aggregate calib. So by pressing the appropriate arrow F8 in the top menu. Now here what's different with regard to the procedure SS endogenous labor. So we have the endogenous variables K, N, debt, tau, P, transfer bar, and beta 1 for our endogenous aggregate variables. Our variables tau n on wage income tax is 28% tau L bar minus the social security contribution rate. So the data by Mendoza, which is used in Trabant and Ulich, estimates tau L bar 28% as the sum of both wage taxes and social security contribution rates. Since social security contributions are absent in the model in Trabant and Ulich, they use the Ramsey model. These two are identical. We have to distinguish these two variables. So in this procedure, we add some new aggregate equilibrium conditions. So for example, in line 1197, let's go to this line, we add the condition that aggregate labor is equal to the sum of individual labor. So in line 1177 and 1178 we compute aggregate labor, effective labor, and in this line 1179 we specify the nonlinear equation that aggregate variable n bar is equal to the sum of the individual labor supplies n nu. In line 1189 we add the aggregate consistency equilibrium condition that the social security budget is balanced, therefore the gas provided for the social security contribution rate tau p must be equal to tau p nu, the one that balances the social security budget for given replacement ratio 0.352. And we add another aggregate equilibrium condition here in line 1241, so let's run through to this line, which is that aggregate capital stock K bar is equal to the sum of the individual capital stock K nu. Next aggregate equilibrium condition is specified in line 1249. Aggregate transfers are equal to the transfers that result from the fiscal budget. Debt is equal to aggregate debt that is provided as our gas is equal to the debt which is equal to the sum of the individual debts accumulated by the households, and The final equation here, equation in line 1253, is our calibration of bidder. So we calibrate bidder such that the return on government bonds 4% is equal to the return on capital. And the return on capital depends on capital income taxes tau k and on depreciation delta. And this is how we calibrate bidder in our procedure SS Aggregate Calib. So we can get back out of this procedure here by pressing F10 and returning to the calling menu. And in line 629 we just solve this nonlinear equation problem. The solution is our benchmark calibration for this economy, and we store the values of the solution in x ag in the variable x aggregate. So this we store these values and save the value for bidder in the variable bidder calib, this and our aggregate and individual policy variables here. Our aggregate government consumption in the variable big G, and we keep it constant through the rest of the computation when we compute the Laffer curve. So for example, we have found a labor wage income tax of 0.191, a social security contribution rate that balances the social security budget of 8.87, and of course the sum of the two is equal to 28%. Our endogenous value of the return on government bonds is 4%, and our mean labor is 0.320, sorry, 0.31, which is close to what we are looking for. And we store our pension for later use and compute consumption, bequest, utility, and so on and so on. So please move your cursor to line 771. Run to cursor. So the in-between lines just store values and print values to the screen, so that you, for example, can see that transfers are 5% of output in our benchmark calibration. And for example, that the old age dependency ratio is 25%, which is not too far away from the value of the US in the present. So all these values are very comforting and very reassuring that we have done a good job to calibrate and specify our model. So next line just gives you how long it took you to compute the stuff. And now in step 8 we compute the Laffer curve. So what we do is we compute the equilibrium conditions SS aggregate for a grid over the wage tax tau n. The grid is from 0.1, from 10% up to 80%. And on this, of course, we have to add the social security contribution rate to get the total tax wedge on labor income. We also have to think of the consumption tax, which also increases the wedge. And we store the results from our computation for the different wage taxes. So for example, for 0.1, 10%, we compute the solution with the help of SS aggregate, where government consumption is kept constant, debt is kept constant. And we find that the social security contribution rate is 0.088661. So our total tax on labor income is 18.86%. And this is graphed in our solution for the Laffer curve. And in the remaining lines we compute the equilibrium values, and in particular in line 811 and 812 we compute total taxes and store these values for later display. We compute total taxes by using the government budget. So in line 809 we compute the transfers, and in line 810 we compute taxes from the government budget and store it in line 811 in the variable results. So our variable results stores the labor income tax, total taxes, and the labor income taxes tau and wage income taxes tau n times v bar, w bar, n bar, that we display as our labor income tax revenues in our Laffer curve. Okay, and so we simply can now jump to the display of our solution, run with the cursor through line 826. So now we compute the equilibrium allocation for different values of tau n, starting from 10% going up to 80%, computing the equilibrium social security contribution rate, the equilibrium total taxes, the equilibrium wage income taxes, and display them in our final graph, in our final picture here, which plots our results as computed with the help of the procedure SS Aggregate. And this completes our computation of the Laffer curve. And now you are asked to do some sensitivity analysis, play around with our program, use perhaps different intertemporal elasticity of substitution, sigma, use a different, or eta, use a different Frisch labor supply elasticity, look at different years, for example 2050, and see how our computation might change at this time due to the demographic transition. So thank you for your patience. This has been really a long tutorial, and I hope you kept on listening for more than an hour. Thank you for your patience. If you have questions with regard to the computation, with regard to the individual steps, please do not hesitate to contact me, and I will be happy to provide you with an answer if possible. It may take a couple of days, but eventually I will get back to you. And thank you for your interest in my book and in my work and in the computation of the Laffer curve in an overlapping generations model.